In this video, we're going to continue looking at solving exponential equations, but in this video, we're going to focus on exponential equations that are a little bit more complex and require a little bit more thinking and rewriting. So let's dive on in and take a look at the two examples below. When I take a look at the two examples below, the first thing I notice is not only that there are x values inside of my exponents, but I notice that I have different bases. And if I start taking a look at my powers resource, what I notice is that I can't easily rewrite these right now. I mean, this says you can't just rewrite one and make them the same. So for example, 32 to the power of 2 is a very, very, very large number. And so I can't just change 64 to be 32 to the power of something. And instead, for these examples that you see on this page, you actually need to change both of the bases. And so if you're unsure of what to do, what I start doing if I can't find a base to just rewrite one of them as, is I start looking for a base that they have in common. And when I start looking at 64 and 32, what I notice is that 64 is the same thing as 2 to the power of 6. So I know that 64 is 2 to the power of 6. And then I also know that 32 is 2 to the power of 5. So because I can rewrite both of these to be powers of 2, if I put these in place with powers of 2, I can actually rewrite these to have a common base of 2. So sometimes you're going to have to rewrite both bases, and then you'll be able to find a common base and then set your exponents equal. So here I start off and I'm going to replace 64 with 2 to the power of 6. And then I'm going to replace 32 with 2 to the power of 5. Now before I can use my common basis trick where I set the exponents equal, I need to make this one exponent. So here I need to multiply 6 times x minus 2, which means I multiply the 6 by both. So I end up with 2 to the power of 6 times x is 6x, and 6 times a negative 2 is negative 12. And then over here, I take 5 times 2x, which becomes 2 to the power of 10x. And now that I have a common singular base, I can now set those exponents equal and solve. So we have 6x minus 12 is equal to 10x. We can subtract 6x on each side. We get positive 4x, divide by 4, and we find that x is equal to negative 3. So if I were to put x equals negative 3 back in place of those two x values, I would make this equation true. Now, let's move on and take a look at this next problem. With 8 being so small, it looks like it might be possible to rewrite 128 in terms of 8. However, if I start to look at my powers resource, what I notice is that 128 cannot be rewritten using an 8. We have 8 to the first power is 8, 8 squared is 64, and then 8 to the third power is significantly larger and something like 512. So I obviously can't use the 8s, and so I have to try and look for a common base that the two of these have in common. So when I start looking, what I notice is that they both have 2 in common. 8 can be rewritten as 2 to the power of 3, and 128 can be rewritten as 2 to the power of 7. And because of that, I will be able to rewrite these to having bases of 2 as well. So here I'm going to replace 8 with 2 to the power of 3. Then I'm going to replace 127 with 2 to the power of 7. We multiply our exponents together, so we get 2 to the power of 12x. And here we multiply the 7 by both, so we get 2 to the power of 7x plus 28. Then from here, because we have common bases, we can set those exponents equal. So I have 12x is equal to 7x plus 28. We then want to get our x values together, so I subtract 7x on each side. And then here, in order to get x alone, I need to divide by 5. So we end up with x is equal to 28 over 5. So this slide is just meant to show you that sometimes we're going to have to change both bases so that they can have a common base, and we can then set those exponents to be equal. So now let's focus on what we do when we have fractions. Now, the first thing that I notice is that the number part in this first problem of the base is 3 and 9. And so I start brainstorming, okay, how can I rewrite this in terms of having the same base? Well, I know that 3 squared is equal to 9. So I'm going to leave this first one on the left-hand side completely alone, and I'm going to rewrite this fraction to be 1 over 3 squared. So now I'm close. I have the same base, but the issue is the fact that I have a 3 in the numerator on the left-hand side and a 3 in the denominator on the right-hand side. Now typically, I like to always have positive exponents, but in this case, in order for me to actually use that property of, well, if we have the same base, we can set their exponents equal, I actually have to have them both have the same base in the numerator of a fraction. So what we're going to do here is we're actually going to take this term and we're going to move it up into the numerator. And remember that when this happens, when we move it to the opposite side of the fraction, the sign of the exponent changes. So on the left-hand side, we're left with 3 to the power of x minus 4. And on the right-hand side, because we're moving this 3 squared up into the numerator, we actually get 3 to the power of negative 2. And while I don't typically like negative exponents, in this particular case, it's nice because now we have a 3 as a common base in the numerator, and because of that, we can set our two exponents to be equal. So here I now have x minus 4 is equal to negative 2. I can add 4 to each side and find that the x value that makes this equation true is x is equal to 2. Now if I look at the next example over here, I notice that I have a base of 49 and a base of 343. And while I can't write them both in terms of 49, I can write them both in terms of 7, because 7 squared is 49, and 7 to the third power is 343. So here I write the 49 as 7 squared, then to the power of x minus 4. And this one becomes 1 over 7 cubed to the power of x plus 2. So I now have a common base, but one of them is in the numerator of a fraction and one of them is in the denominator. So what I'm going to do is I'm going to rewrite this one with the fraction and move the 7/3 up into the numerator. So here I have 7 squared to the power of x minus 4 on the left. And here I now have 7 to the power of negative 3 raised to the power of x plus 2. Then from here I can utilize the powers to powers, so this really becomes 7 to the power of 2x minus 8 is equal to 7 to the power of negative 3x plus a negative 6, or minus 6, however you like to think about it. Remember that you have to multiply both terms by that exponent attached to the 7. Then from here, because we have common bases, we can set our two exponents to be equal. So we have 2x minus 8 is equal to a negative 3x plus a negative 6. I add 3x, add 3x. So I get 5x minus 8 is equal to negative 6. I add 8 to each side. So I end up with 5x is equal to 2 divided by 5. And I ultimately find that x is equal to 2/5.